Okay, so so let's start talking about the Jacobi method then. So the Jacobi method is basically looking at for solving heat equation. Okay, so let me just first write down the matrix equation. So I have A that is equal to, let me write it that way, minus 2 over delta x, 1 over delta x squared, etc. So I have a tridiagonal system. Okay, I have a F equal to F1, Fn, so it's an n by n system. And I want to solve Ax plus F equal to 0. Okay, so the Jacobi method is analogous to wanting to solve the equation dx. Well, let me just write it in OD because this is already a discretized system, Ax plus F. And I want to discretize this using discretize using forward Euler. So basically, I have x of let me use k for the time step or iteration number over delta t equal to ax plus f, or axk, right? If it's forward Euler. Okay. Now the question is, what should I choose in terms of delta t? What's the proper choice of delta t? Yes?
Highest possible delta with a stable
So as one answer is, I want to choose it to be as high as possible as long as this whole thing is still stable. Let me try that choice, and you're gonna see what problem am I gonna get. Okay, so how do we figure out what's the maximum delta t so that the whole thing is gonna be stable? Fourier analysis is actually one way to analyze what's the maximum delta t if you have a periodic domain, right? So actually, for this matrix, to actually get to a periodic domain, I have to put something here and something here so that it's a periodic domain. But like, what if I just don't have these two entries? What if I just have a normal zero boundary condition? What's the best way to analyze the stability? Eigenvalues, yes, that's right. So the way to figure out is to figure out the eigenvalues of A. A is equal to U times lambda times U inverse. Well, actually, in this case, A is a symmetric matrix, so I can well write U transpose here, right? So for a symmetric matrix, the eigenvalue decomposition is the eigenvectors are orthogonal to each other. So I can have U inverse or U transpose. It's it'll be valid all the same. So now if I apply that decomposition over here, which is going to get me x of k plus 1 minus xk divided by delta t would be equal to U lambda U inverse times xk plus f. And then there is an opportunity to multiply both sides by U inverse, right? Okay, so, and I can denote this as yk. So if I denote this as yk and denote U inverse xk plus 1 to be yk plus 1, what I get is yk plus 1 minus yk. I'm just multiplying both sides by U inverse, right, times the whole thing. It's going to get me this is equal to my lambda, which is a diagonal matrix, times yk plus U inverse times f. I diagonalized the system. Alright, now it's easy to figure out this is actually delta t, not delta x. So now it's easy to figure out what is the maximum delta t I can take, because I have n decoupled scalar equations, right? So what's the criterion for my y to not diverge?
Highest eigenvalue times delta t should be
the highest lambda times delta t should be less than 1 or something else, right? So let's actually write down this. So y of k plus 1 would be equal to yk plus delta t times lambda times yk plus something, right? So if you lump these two together, it's actually 1 plus delta t lambda times yk, right? So if you look at this, as long as 1 plus delta t times lambda is not well, okay, so let me first say here, all the lambdas here are negative. Okay, so if you look at A here, so if you as long as 1 plus delta t times lambda is not less than minus 1, I'm going to be having a non-divergent scheme. But is that what I want? If I choose it to be exactly the as large as possible one, then the eigenvector that corresponds to that to that lambda that makes this amplification factor to be minus 1 would be oscillating, would be multiplied by minus 1 every iteration, every time step. So that's actually never going to decay, right?
slightly lower value than.
Right. So basically, you need a lower value than this, right? Okay. So basically, what Jacobi method has been saying is that. So let's actually look at the spectrum of this and figure out what it is. So let's actually construct the matrix A. Let's actually, for example, give me an n equal to, let's say, 100. All right, dx is equal to 1 over n, and my matrix A is always going to be minus 2 times identity of n divided by dx squared plus diagonal of 1's minus 1 1, and then plus the same thing, but I'm going to be making it minus 1. All right, so yeah, so basically this only shows the very end of the matrix A, but like it looks like it's what we expect. So if you look at the eigenvalue of A and plot it, so that's what it looks like. Okay, so it goes from something very close to 0 all the way to about minus 4 times 10 to the 4th. Since our delta x is 0.01, 10 to the 4th is basically 1 over delta x squared, right? And we get minus 4 times that. Okay, and so what the Jacobi method do in this case is actually to take a time step size such that the amplification factor for the very
The most negative.
yeah, for the most negative eigenvalue is going to be basically let me see. Right. So the most negative eigenvalue is actually not going to be exactly minus 4 times 10 to the 4. So basically what Jacobi method does is that it takes the time step size so that the whole range from 0 to minus 4 times 10 to minus 4 is going to be lying exactly in the region of minus 1 to 1. Okay, so let's you can zoom in into this to see a little bit about what this is. It looks like it's very close. The first one is very close to minus 4, but it's actually a little bit above that. All right. Okay. So it's essentially taking a time step size that maps delta t maps the lambda that lies in -4 e4 to 0. Well, it's actually not including them, to -1 and 1, right? So to 1 plus delta t lambda within this. So this is the amplification factor, right? So this is how fast, how much smaller the next iteration is getting, right? So this is basically almost the maximum step size you can choose while still being stable. All right.